Hello, maurieo. This is a small introduction to using the total station in a practical sense. It's a sort of a guide to a little practical exercise that I'm proposing, and that is why you're watching this, so that you can get an idea of what you're up for when you go out in the field with maurieo. So let's just have a look at the total station and what it does. Basically, the total station, one way or another, does three things. It measures horizontal angles, it measures vertical angles, and it measures distances. From that basic information that it collects, it is able to calculate some other information, such as horizontal distances, differences in height, and what have you. Now, one of the first things we need to understand about the total station is the concept of face left and face right. Face left is the main face or orientation that we have the total station in. When a total station is in face left, when you're looking through the instrument from that end of the instrument, the vertical circle, or the sort of thickened part of the total station, will be on your left, and that is called face left. Usually the knobs are quite in a comfortable position, and usually at the front of the instrument as well, so that you are able to quite easily turn the clamps on and use the slow motion screws, both vertical and horizontal. So things are quite readily available. Face right, then you flip the telescope through 180 degrees and turn the whole theodolite through 180 degrees, so that you are now looking through it, and the vertical circle will be on the right hand side. The knobs for your slow motion screws and your clamps in some theodolites tend to be at the front of the theodolite, at the objective lens end, and they're slightly less comfortable to use than when it's in left face. The majority of work is done within left face, except when we were doing accurate readings, and we do accurate readings when we are doing, like between our traverse marks, we would do accurate readings on both left face and right face. The concept here is exactly the same as with when we use a spirit level. If we check it, we would first of all put it on a level surface, check that it's level, and then spin it through 180 degrees and check that it's still level. If it's not, if the bubble is not showing level in those circumstances, we then know that there's an error. And the face left, face right concept is pretty similar to that. If the theodolite has a slight tilt in any one direction off the vertical, then taking a face left reading and a face right reading and meaning them will give an accurate result. Ideally, we keep an eye on the difference between our face left and face right readings, as this tells us that our instrument is going a little bit out of adjustment. So when we find that the difference between face left and face right is consistently annoyingly large, that's the time to go and get the instrument serviced, if the actual annual servicing date hasn't come up. Now, for accurate angle measurement, angles are measured on both face left and face right for removing these verticality errors. The face left and face right readings are meaned. Now, let's just have a look at a situation that I'm proposing for the practical that you are going to be doing. If we set our instrument up at A, and we would put what we call a backsight or a prism on B. Now the green B is a known bearing. We know the bearing between A and B. So we set up our instrument at A, and we are able to set the bearing to B by pointing it, and there's a number of different ways for each each instrument, but if we were to set the instrument at A and point it accurately to B, and then we can push a button, in the one particular one we use called the H set button, and that enables us to type in the bearing 87 degrees 56 minutes 30. Set that bearing. I would recommend that after you've set that bearing, you spin the theodolite through 360 degrees and commence your first reading. And this is what I've done down here. This is a sample out of what I would think that your field book would look like for this exercise. So the first thing to do is to point it and take a reading to B. Now, just standard observing procedure is that you would line with the gun sight at the top of the total station, you would line the instrument roughly up, pointing to the prism on B, and just gently tighten the clamps. You caress them. You don't need to put any amount of force on them. They just need to be there so that they can stop the instrument moving off the mark. Once you've got the clamps gently tightened, you can then use the tangent screws or the slow motion screws to move the instrument accurately onto the mark, or to bisect the mark both in the horizontal and vertical directions. For the tangent screws, you always turn the screws so that you are tightening the screw. If you go the other way with their spring-loaded screws, usually there's potential there for there to be a bit of a lag, and that you point it and then the spring clicks into place and you're actually not bisecting the mark as you had thought. Once you have completed your observation, you then unclamp the clamps for both the horizontal and vertical clamps, and then you're on and looking at the next mark. So first of all, then, just to recap, we've set our bearing to B, spun through 360 and taken a reading to B, 87 56 10. Then take a reading to C, 236 07 12, and to D, 332 27 18. They are all on face left. In this instance here, I have then put the instrument onto face right and taken a face right reading onto B. That reading would be 180 degrees different from the initial reading. So 87 plus 180, 26. Note the 8, 2 plus 6 is 8 there. We then mean the seconds. So 10 plus 20 is 15. And the actual bearing we wanted to set was 87 56 30. So our accurate reading suggests that we've only got 87 56 15. So we would add 15 seconds to make it up to 87 56 30. That 15 seconds is the correction that we will then apply to the other accurate bearings to C and D. We then continue on. It's usual to be doing this in your head and writing this in as you go. We would then continue on and do their right face to C, which is 22 there, which we would then mean as 17 seconds, and then to D, 18 and 32 is 25 seconds. We then, once we have completed our round, this is called a round of bearings, we would then add our 15 seconds to each one, and this would give us our 236 07 32 and 332 27 40. In this instance, this is all we're doing at this particular, for this setup. We are not doing any further adjustments resulting to the angles at this point. That is beyond the scope of this particular practical. So what I would do then is notice here that 236 07 32, we would normally, for this distance here, which is 232.17, we'll just round our bearings to the nearest 10 seconds. So that's just I've rounded it off there, underlined them to show that they're complete. Note that once our bearings, we've finished and reduced our bearings, we write the finished or reduced bearings onto our diagram. So in our field note, we would always be drawing a diagram. So the next, as we were going through these, I might add that as we're doing our observations, we are also measuring our distances on face left and face right, and meaning those, and then rounding them to the nearest 2 decimal places. So that's sort of a round of bearings that we have done in that particular case. So then from there we move on. Now the other thing that we can do is we can also do, I'll possibly just go back to there, I think, at this point here. Another thing that we could do once we have set up these are to our survey marks, we may wish to do some topographical work, and any topographical work that we would do would be done on face left, and we would just be measuring the bearing and distance, and possibly the difference in height, after we've obviously noted our height of our instrument and our height of poles and things such as that. But they tend to, all that work, or when we were doing topographical work, we are doing it on face left. There's the expectation that face left, of course, is reading the correct bearings. Obviously the ones on face right will be 180 degrees different. So let's just now move to my second layer again. Now, one of the other little exercises that we were going to be doing with this in this little practical is to set out a peg at right angles accurately. Now, I've put here a little diagram and a little operating procedure that we would go through to set out a peg at right angles accurately. Sometimes we might not follow this procedure in quite this manner. We may just do it perhaps on left face and check it on right, depending how well we know our instrument. So here we would go, we were set up at A and B, doesn't really matter which one they are, and we can set a back bearing, if you like, although it's not a bearing set because it wouldn't be true, it's an assumed one, but we can set 0 to B so that the theodolite is reading 0 on B. And again, we would just spin it through and make sure that we're checking that we have got it set fairly accurately. Spin it through 360 degrees and just check we've got our 0. We would roughly turn off our right angle, which of course would be 90 degrees, naught if we were going out to that side, and we would just possibly put in a peg, make a mark, a hole, and put the peg in. Remember, we were just setting out the line of the right angle, no particular distance. Now, we would be doing this on face left, and on face left we would put a mark on the peg, possibly if we were using a prism or a sharp, the sharp end of a prism or pole, or possibly even a plumb bob, we would mark the face left. We would then turn the instrument through 180 in both vertical and horizontal, and again set 0 on B on face right, set out our 90 and make another mark on the peg. Now, in most circumstances the two marks on the peg occur in the same place. If the difference between the two was any more than 5 millimeters, I would have some concerns about the accuracy of the instrument or the accuracy of pointing and what have you, and possibly that would be an indication that it needs to be sent in for service. And nonetheless, we would have our two marks there, and the actual mark, or the actual position, the 90 degree position, I would go halfway between the two marks. That's because of the left face, right face thing, and it's halving the error. So we mark position C on the peg halfway between the C left face and C right face. And then, just as a final check, because we're trying to do this very accurately, I would observe the angle. So I'd do a round to the angle, so face left, and I've done this here, face left to B, and we've meaned them there. In each case they've come out the same, we're almost perfect, and as is always the case when maurieo's on the job. And of course we subtract our 17 seconds to bring them back to 0 to show that we've got a right angle. Now, and we check that it's in retirement. It's in a perfect world, that's how it would be, but sometimes it's not. And then we just need to know, it's dependent on how far away our peg is, what an error of say 20 seconds represents at that distance. So we might calculate that in our calculator using a tan function, or just, be aware that it's okay. If it's 10 seconds out, it's only out 3 or 4 mils, which is maybe acceptable depending on the type of job. I have mentioned earlier topo shots, and I've covered it again here. Obviously, for topo shots where we're going to record the height, obviously we need the height of the instrument and the height of the target usually being a prism pole, and quite often the poles are set so that we can have a set target height of, say, 2 meters is quite a common one. And these are usually recorded, these topo shots, on face left only. We usually give them a point number, a bearing to the nearest minute, distance to the nearest centimetre, if that's possible. Sometimes we're recording this stuff electronically, so we get everything to the seconds, and the difference in height again, and a code. We need to know what it is. In this case I've put manhole, MH, but it could be spot height, edge of concrete, top of bank, bottom of bank. There's all sorts of issues here. Now, most of today's total stations have the ability to measure in what we call the reflectorless mode, which means they do not need a prism. They can just measure to a flat surface of a building or something. Quite good for inaccessible areas. Also quite good for measuring to power lines, because we don't have to physically touch the power line. Provided there's sufficient width there, we can measure and calculate clearances and what have you. The problem with the reflectorless measurement is that it sometimes requires that the prism constant in the total station be changed to 0, and quite often what occurs is we forget to change it back again, so it affects subsequent measurements. So when using the reflectorless mode, be very careful and make sure that you change the prism constant back to where it should be. And in fact, for all measurements, make sure that you have the correct prism constant, as there is quite a variety of them. The prism constant is a constant amount that is added and subtracted to the distance measured by the machine to make it to correctly reflect what the true distance should be. So there you are. This is going to be a small practical exercise in which you will be introduced to the total station, recording field notes, possibly checking a few bits and pieces, doing some topo shots and a little bit of reflectorless stuff, so that you have a fairly good idea of the range of things that a total station in the hands of a competent surveyor can achieve.